particular telescopes, which I'll get into shortly. And one of the reasons why we've had such a big jump in the gap was the launch of the Kepler mission. Kepler is a space telescope that was launched in 2009 and is responsible for the discovery of most of the planets on this graph. So about 75% of known planets today were found by Kepler, and that was all in the last 10 years or so. So the way Kepler works is that the way Kepler worked, it no longer is functioning, is that it monitors the brightness of stars. So it takes images of stars over and over and over, and it counts up how much light is reaching the telescope from the star at every image. And what it looks for is small decreases in the brightness of stars when the planets go in front of them, if they happen to be lined up with our line of sight so that their orbit goes between the star and our telescopes. And what you see in this time series, we call this a light curve, the brightness of the star versus time, is these dips that happen periodically. And if we see this happening, we can infer that perhaps there's a planet orbiting around the star. So this is how Kepler was able to find thousands of planets, as it's been able to do. And not only by doing this with one star at a time, Kepler was able to find so many planets because it could observe many, many stars all at once, over 200,000. So you can imagine if you just look at this large field of view that Kepler was staring at over and over and over again for about 4 years, every single one of these stars got one of those time series, and we were able to search each of them for planets around them. So as a result of the major advancements that we've learned from Kepler, we now know that planets are common in our galaxy. There are more planets in our galaxy than there are stars, and on average, each star hosts several planets. So we can now ask different questions. Instead of just are planets out there, we can start asking questions like, what are these planets like, and whether they're anything like the ones in our solar system. And perhaps most excitingly to me, are any of them hospitable to life like we have here on Earth? Really, I'm just here to find aliens. So the main problem with Kepler is that most of the planets that it found orbited relatively faint stars. So this is an image from the digitized sky survey, which was taken at Palomar Observatory in the 1950s. And this is just a photographic plate of, lots and lots of stars. And this one in the center here happens to be one that was observed by Kepler and found to have, I think, at least 6 planets around it. And that's a wonderful discovery. It made front page news back in 2011 when it was released. But what you'll notice is that this star is pretty nondescript. It's fairly faint compared to even the other stars in the general vicinity, and it's nowhere near one of the brightest stars in the sky like the ones that we can see with our naked eyes. And that's a problem, because if we want to study these stars in detail, we need lots of light from them. Really, we want to be looking at stars that look like this one. This is a star that you can see with your naked eye, and it just blows out this photographic plate like it was taken. So this is the main challenge with what Kepler was able to do. Kepler looked at only a small patch of sky, and that's great if you want to find lots of planets. But if you want to find planets around the brightest stars, the closest stars to us, you need to look at all of the sky, because the brightest stars to us are all around us. We're within the nearest stars in the sky. So instead of looking at one small area of sky like this, we need to look at the whole sky. And that's why we have built the new Transiting Exoplanet Survey Satellite, which we call TESS. This is NASA's new current planet hunter, and is effectively the successor to Kepler, designed to fix this exact problem. The fact that Kepler was really only looking at faint stars with planets around them. TESS is going to perform a survey, and has performed a survey very much similar to Kepler, looking for planets using the same method, looking for these dips in brightness. But instead of looking at only one small part of the sky, looking at almost the entire sky over the course of several years. So back in 2018, TESS was launched. These are some images from the launch. Here's the Falcon 9 fairing that TESS was sitting inside of. What's funny to know is that TESS is actually very, very small compared to this fairing, maybe about, smaller than this sticker of TESS on the side of it. But it had to be in there because it needed that relatively large rocket to send it into its unusual orbit, which lets it observe stars with relatively little interference from light from the sun. Here's me. I was at the launch. It was pretty awesome. I recommend if you ever get a chance to go to a launch, make sure you try to do so because it was great. And this is the Falcon 9 rocket back here with TESS right at the top. And here's what happened. It was the second launch attempt when it actually went up. We started off the week hoping for a launch on a Monday, and we were about to get on the buses. In fact, I was on a bus to the launch site to watch, and they called us back off and said, oh, we're not launching today. We want to do some last calculations before we go. So they pushed it back for 2 days, but it was well worth the wait because 2 days later, we got this perfect launch. Everything went beautifully. The orbit was exactly the way we wanted it to be. And SpaceX even was able to land the booster stage on a barge in the Atlantic Ocean. So it was a great day. And within a couple of months, TESS started sending down some of its images. So this is the first field of stars that TESS observed. And you'll notice that this is a very large area of sky that TESS is looking at. So this is the Large Magellanic Cloud. This is the Small Magellanic Cloud. So just to put a sense of scale, you can see these with your naked eyes very easily in the Southern Hemisphere. So TESS is looking at the very large area of sky. And look at all of these stars in these images. And once we got these images down, we started taking a look at them, and a couple of individual stars stuck out. So now I'm zoomed into camera 4. This is the one down here at the bottom. And I'm going to zoom into a particular star over here called Pi Mensa. And it's this one right here, this brightish star, not the very brightest star that you see in this image, but one of the brighter ones. You can see it stand out from its neighbors or right around it. And Pi Mensa has already been known as an interesting exoplanet hosting star since 2002. So when we took a look at the TESS data, we were not necessarily expecting to see this planet because we didn't think that it was likely to have its orbit aligned so that we could see it. But we did see something very interesting. Oh, interestingly, I've lost my, okay, here we go. So here's the image, here's the light curve, the brightness of the star over time as a function of time that we did see. So we saw a small dip that repeated over and over again every 5 days or so around the star. And this is work that was led by Chelsea Wong. She was at MIT at the time as a postdoc. Now she's a professor at the University of Southern Queensland in Australia. And this is her dog, who is named Kepler, not to be confused with the telescope. So TESS reveals orbiting Pi Mensa. In addition to the known planet that we'd known about for over a decade by that point, there's another planet, a smaller planet, which we now call Pi Mensa C. It orbits much closer into the star than the outer planet, and is much smaller and much lighter weight. We were very interested by this, and as soon as we saw the data, Jen Burt, who is a scientist at NASA's Jet Propulsion Laboratory now, but who was also at MIT at the time when we were doing all of this, started working on trying to analyze some older data, which would have been used to discover the original planet, to see if we could see that second planet that TESS had found in there. So we took data from the HARPS instrument, which is located in Chile, and the Anglo-Australian telescope, which is located in Australia, as you can see by these kangaroos, and combined it together. And we were able to confirm this planet around Pi Mensa. So this was exactly the type of planet that we hoped to find, or the type of star we hoped to find planets around. This is what Pi Mensa looks in those same photographic plates. And you can see there's a lot of light coming from this. And this gives us the opportunity to make really interesting and really detailed measurements of this planet. We can study its atmosphere, and we can study its orientation, how its orbit is aligned with respect to its star, and get some really interesting clues about its formation. So this was a great start. This was literally the first planet that we found with the telescope as soon as we turned it on. And in that same first month of data, there was another really interesting one. And I'm going to zoom into this one. So this one's in camera 3 over here. And we're going to zoom in a little bit further. This is not nearly as bright of a star, but it's actually very nearby. It just happens to be an intrinsically faint star, a red dwarf called LHS 3844. But it's actually one of our nearest neighbors. It's only about 15 parsecs away from us, or about 50 light years. So this is work that was led by Roland van der Spek, who's also at MIT. So here's the TESS light curve for this particular star, LHS 3844. Again, we see this characteristic brightness curve, this light curve that shows the brightness of the star constant for a while, then it dips every few hours or so. 11 hours is how long it takes this planet to go around its star. So it's orbiting very, very close to its star, much closer than any of the planets in our own solar system. And from this, we can infer that there's a planet about 30% larger than Earth orbiting around the star LHS 3844. And I mentioned this a little bit earlier, but this is a tiny star. So this is a 2-scale image. This is a real image of the sun. This is not a real image of LHS 3844, but the size of the star and the color are relatively to scale. So this star is about only 20% the size of the sun. And that means that it's really advantageous for us to study planets in the system. When we study planets, we're usually competing against the brightness or the light of the star and trying to tease out very small effects due to the star or due to the planet on the star. If you have a small star, that means the effects of the planet are bigger by comparison. So this is a particularly useful one to study. So the question that we wanted to ask is, does this planet have an atmosphere? It's orbiting very near a small star. And we don't necessarily know if these small stars are good places to keep planets with atmospheres. One reason is they flare. So this is what a flare looks like on the sun. This is on the left. So you get this kind of burst in brightness right there. The flares that we see on little small stars like LHS 3834 are much, much bigger and potentially much more devastating to atmospheres. So can atmospheres survive at all? That's what Laura Kreidberg, who at the time was at the Harvard Smithsonian Center for Astrophysics and was collaborating with us at MIT. Now she's the director of the Max Planck Institute in Germany, wanted to know. So Laura was asking, does this planet even have an atmosphere at all, or has it just been totally blasted away by billions of years of flares impacting the planet? So we observed this planet with Spitzer, the infrared space telescope that NASA launched in the 2000s that has now been retired and replaced with the new James Webb Space Telescope. And what we found was that Spitzer indicates that there's probably no atmosphere on this planet. The planet is so hot on its day side and so cold on its night side that there doesn't seem to be any heat moving from the day side to the night side, which is something you would expect if there was an atmosphere. The winds would carry the temperature around. That's what we see here on Earth. The temperature doesn't really change that much between day and night here on Earth because we have an atmosphere that keeps everything relatively constant. Whereas on the moon, there's a big difference in the temperature on the day and the night side. So based on this, we infer that LHS 3844b probably has lost any atmosphere that it once had, which is a little bit worrisome if we're hoping to find planets around similar stars that might be good places for life to exist. If the very close-in planets around similar stars can't hold on to their atmospheres, can the ones in the temperate zone, the place where there might be liquid water on their surfaces where life could exist the way we know it, can those hold on to their atmospheres as well? That's a big open question. But so far, the evidence has not been particularly encouraging. All of the planets that we've looked for with similar characteristics seem to have no atmosphere left to speak of. So that's one of the big questions we have going forward. Can planets like this even hold on to atmospheres and therefore be good places to live? So these are two really interesting planets that we found right off the bat, right at the very beginning of the TESS mission, both in the first month of data. And since then, we've had a lot more time to observe the rest of the sky, and we've been able to fill in most of these observations. So here's the same image here, this little strip here, and I've put it now into celestial coordinates, and that's this kind of stretched thing over here. And I'm going to go ahead and click go on this video. So over the last 5 years, we've been continuously observing the sky with TESS, and we filled in a large fraction of the sky. So in the first year, we spent on the southern hemisphere, then we went to the northern hemisphere, then we went back to the southern hemisphere. So we're still marching across here, trying to fill in these gaps. Then we kind of filled in this gap here in the center, the ecliptic plane. And we're working on filling in this hole here. The reason why we haven't completely filled this hole in yet is because Earth happens to be, unfortunately, right around here as it appears from TESS's orbit, and Earth is very bright, so we try not to look here. Over time, this will change and Earth's location will move to other parts of the sky, so we'll be able to fill this in. We just haven't quite gotten there yet. But we filled over 90% of the sky now, and therefore we're starting to find planets like this all over the sky. And we're learning tons and tons of new things. Some statistics are that so far we've found 6,700 planet candidates at least. And we think that most of these are probably real planets. We just haven't had the chance to go through and systematically confirm them and rule out the false positives yet. A fraction of these will be false positives. Not all of them are going to be real planets. So far, we've confirmed almost 400 of the 6,700. We're working on trying to speed this up because otherwise it'll take us too long and we'll just keep finding more planet candidates before we are able to confirm them all. So this is going so far so good, but we're already finding really interesting stuff. And some of the groundbreaking discoveries that we've been, making are like the ones that I showed earlier, the ones kind of about planets that we expected to find, planets like the ones from Kepler, just orbiting nearer stars to us so that we could study them in more detail. But we've also found some things that we just didn't expect at all, which is really exciting. And that's what I want to talk about for the rest of my presentation, is TESS has given us the opportunity to answer some questions we weren't even necessarily thinking about asking, like what happens to planetary systems after the stars they orbit run out of hydrogen fuel and die and leave the main sequence. So this is an interesting topic that I've been studying for a while now. I've kind of gotten more and more pulled into this as we've studied more and learned more and more about planets around dead stars. And one of the key ideas is that right now, our sun is burning hydrogen fuel and using that to produce light, which keeps us warm and which keeps, the climate on Earth going and keeping it relatively constant. But that won't last forever. Eventually, the sun will run out of its hydrogen fuel and it'll no longer be able to continue burning hydrogen the way it does now. And when that happens, eventually the sun will turn into something called a white dwarf. A white dwarf is a stellar remnant for stars like the sun. More massive stars, the very, very most massive ones, will turn into other things like neutron stars or black holes. But the vast majority of the stars in our galaxy, and by extension, the planets, the stars that host the planets that we know about, will become white dwarfs. So when I made this graph, it was about 99.7% of the planets that we know about will eventually orbit a white dwarf. So how does this process happen? Well, let me show you some images of the sun today. And this is just an image I grabbed from this SDO, the Solar Dynamics Observatory satellite. What I'm going to do now is I'm going to zoom out and I'm going to look at this from a very wide angle because eventually the sun is going to get very large. So when the sun runs out of nuclear fuel, the first thing that happens is that it puffs up and becomes a red giant about 10 times its original size. And this is because when the sun is burning fuel like normal in the core of the star, it's actually fairly well self-regulating. But as soon as it runs out of fuel in the core, it starts burning fuel in shells. And those shells are not as self-regulating. And as a result, even though it's running out of fuel, it starts burning fuel faster and faster and faster. And that's what causes it to puff up and get bigger and brighter. And this process continues. And eventually, the sun puffs up to about 200 times its original size. And this is a very brief phase, but the sun becomes extremely bright when all of this happens. And it stops when the sun starts burning helium. When the sun gets so hot and everything collapses down so much that the core of the star becomes strong enough to burn helium, it'll collapse back down and become a little bit self-regulating again for a little while. But helium burning is not as efficient as hydrogen burning. The nuclear reactions that cause helium to fuse into heavier elements just don't have as much oomph as the reactions that cause hydrogen to fuse into helium. So this is not a good long-term solution. And eventually, not that long afterwards, the sun is back to where we were before, puffing up again until as it runs out of helium. For the sun, this will be the end. more massive stars will start burning more and more elements. Will keep performing this dance up and back. But for the sun, this is where it all runs out, and nothing more can be burned. So when this happens, the outer layers get shut off. They produce these beautiful planetary nebula that you've probably seen images of, either from the Hubble telescope or the James Webb telescope, or even from your own telescopes in their backyards. And in the center of these planetary nebula are the leftover cores of the stars, which will eventually become white dwarfs. So the white dwarfs are the burnt out cores of stars like the sun after they run out of nuclear fuel and they shed their outer layers into the rest of space. So typically these stars are about the size of Earth at this point, but they have about half the mass of the sun. So they're very, very dense. They're roughly the volume of Earth, but they pack in about 300 times more stuff than Earth does. And over time, these stars cool down. They go from hot blue things to cool red things, and eventually they'll turn into, light, things that don't even produce light anymore. We call those black dwarfs, although our universe is actually not yet old enough for any white dwarf to completely run out of its thermal energy and cool down so much it doesn't produce any light anymore. Every white dwarf that's ever been formed is still glowing with the leftover heat from its nuclear fuel. So over time, these white dwarfs shrink and cool down, but still they're all in the relatively warm phases of their life cycle at this point in the history of the universe. So this is something that we've understood for a while based on the physics of stars, but a new frontier is what actually happens to the planets during this process. So let me do the same, show the same kind of plots or the same kind of animations, but now I want to put the planets in our own solar system on top of it. So immediately what you'll see when I expand out the sun is that it's going to be a very bad time to live on Earth if this happens. So Mercury, Venus, and Earth are all likely to be either engulfed or totally torched by the expanding sun as it runs out of fuel. Although the planets further out will get a little bit hot, they will survive. So Mars should make it, and anything beyond Mars, the asteroid belt, Ceres, Jupiter, Saturn, etc., those all should survive relatively unscathed, at least to start off. One thing that does happen, though, is that when the star sheds its outer layers and produces the white dwarf, that causes the gravity of the star to weaken because there's less stuff there holding everything in. And it's lost a lot of its mass. So the orbits of the planets move outwards as a result of that. But in principle, they should survive. And we actually have evidence of this. So this is an image taken by the Spitzer Space Telescope of a white dwarf called WD 0806-661. And it's this object right here, this dot in the right-hand side. And this thing over here happens to be a planet orbiting it. It's very massive. It's relatively hot still because it's so massive. That's why it was able to have this nice image taken by the Spitzer telescope. But it is in fact a planet. And it's orbiting around the star at a very large distance. You might be wondering, how do you pick out this one here as the companion to this one when there's so many other stars nearby? It turns out that these two are both moving relatively fast through the galaxy compared to the background stars, and they both seem to have exactly the same motion, so they must be traveling together and orbiting around each other. So planets that orbit further than about the distance of Earth to the sun, which we call 1 astronomical unit, will survive this process of the star evolving from a normal main sequence hydrogen burning star like the sun into a white dwarf. Sorry. But do these planets ever move backwards? Can they come back close to the white dwarf afterwards? And if they do that, can they survive the journey back in? And that's what TESS has given us some interesting insights about. So this is a TESS light curve of a white dwarf called WD 1856 plus 534. I apologize for all of our astronomical phone numbers that we throw around. I'm sure it can be very confusing. It definitely is for me when you have all these numbers. But that's the best we can do in terms of names. So here's the light curve that TESS measured for WD 1856 plus 534. You see this clear dip in the center. It's a little bit noisy. That's because white dwarfs are very faint, and because they're no longer producing their own light, they're from fusion. They're just glowing from the leftover heat. But there's clearly something going on right at the center here. And one of the really interesting things about white dwarfs is that they are very small. So anything going in front of them is going to cause a very large drop in the brightness. So we took some observations from a telescope on the ground, the Gran Telescopio Canarias. I like to say that this was a 10 centimeter aperture telescope, because TESS's telescopes only are about the size of a camera lens, 10 centimeters. And we wanted more light, so we swapped out our 10 centimeter apertures in space for a 10-meter telescope on the ground and increased the amount of light that we gathered by a factor of 10,000. So it was really make it possible to get this beautiful light curve of this transiting planet. So when we took this data from the GTC and we modeled it, what we found is that this is consistent with a Jupiter-sized object orbiting the star. And that's really interesting because Jupiter-sized things could imply that they're planets, but that doesn't have to be the case. And the reason for this is that there's a lot of different things that are the size of Jupiter. If you see something the size of Jupiter, in general, it could be a giant planet like Jupiter, which you would think would be the kind of most obvious explanation. So with the size roughly the radius of Jupiter, it could have a mass somewhere from about a quarter of Jupiter to about 10 times the mass of Jupiter, and we would still call all of those things planets. But there's other things called brown dwarfs that are a little bit more massive than planets. They're massive enough that they at one time fused deuterium in their cores. And those are also about the size of Jupiter. And even the very lowest mass stars, the very smallest red dwarf stars that have masses between 80 to 120 times the mass of Jupiter, all have radii relatively similar to that of Jupiter. So if we see something the size of Jupiter, like we do around WD 1856 plus 534, we can't really say what it is until we know what its mass is. That's the way we have to distinguish it. We have lots of tricks in our toolbox for trying to figure out what the masses of planets orbiting distant stars are. And the one that we usually use is called the Doppler method. So what we try to do is we make spectroscopic measurements of the star. That is, we take the light of the star and we split it up into different colors. And we look for little dips in the brightness at different colors, which correspond to wavelengths where certain elements have atomic transitions. And if you watch these locations, these dark bands throughout the orbit, if you have a massive object, you'll see these dark bands move back and forth as the Doppler shift, the motion of this object is causing the star to jerk around, move back and forth, and show us the color changing. The color changing here by the Doppler shift is essentially the same as the pitch of sound changing, like when an ambulance goes towards you and away from you. It's the same exact physics here. So this is the way we normally try to study companions to planets. Unfortunately, this particular white dwarf is very old. It's actually been a white dwarf for longer than our own sun has existed. And it's relatively cold. It's colder than the sun, cooled to about 4,700 degrees Kelvin. And white dwarfs of this age and temperature have none of these dark bands that we can study. So we can't use this method at all. Instead, we had to use a different method, which is looking for the heat of this planet. So the way this works is we know that the more massive an object is, the longer it will hold on to its heat. That kind of makes sense, right? If you have a very small, if you have a very small chunk of ice and you drop it into a glass of water, it'll melt much faster than if you have a really large chunk of ice. Same idea. If you have a very small planet, it'll cool off faster than a very big planet. And we think the planets start off fairly hot when they form. So we observed this planet with Spitzer, and we tried to measure how much light was blocked in both optical light using our data from the Ground Telescopio Canarias and also in infrared light. And in the infrared, what we were looking for was to see if there's any light that's contaminating the brightness of the star from the planet itself. And we found none. And that means that the planet has to be very faint and therefore very low mass, because if it were higher mass, it would still be warm and we would see the glow from its heat. But we don't see that, so we can constrain the mass to be less than about 12 times that of Jupiter. And if you go back to my handy chart here, if it's less than 12 times the mass of Jupiter, then it must be a planet. So we call this likely to be a planet, and we call it WD 1856b for short. So this is a really weird system. This is what it looks like to scale. So you've got your little tiny white dwarf over here, and then not that far away, you've got your giant planet, which looks like Jupiter, which is 7 times larger than the white dwarf. It's kind of an unusual thing to think about a planet being bigger than its host star, but in fact, that's what we see here. What's really interesting, though, is that this is what it would have looked like when the sun, when its host star was on its main sequence lifetime like the sun. And this is to scale. So if this planet were orbiting where we see it today, it would have been just barely grazing the surface of the star, very, very close in, much closer than any of the planets in our own solar system are to our sun. And what's even more surprising is that if the planet is here now, presumably it must have survived the time when the star puffed up and became larger than its current orbit. So how is that possible? What we think actually must have happened is that originally this planet was orbiting much further away from its star and then later came back inwards. So we think that originally when the star puffed up and became a giant like that, the white dwarf, the planet orbiting the white dwarf had to have orbited a little bit further out than that even. So originally we think it had this relatively large orbit far out and then had to migrate inwards. And this would have been a bad time to be any of the inner planets around this white dwarf as well. They all would have been engulfed, whereas this particular planet would have survived perhaps just barely because it was far enough away. So there's a couple of different ways that you can explain how this planet could make it inwards, and I'm going to talk through a couple of them. So the first idea that we had to try to figure out, how do you get a planet from far away inwards towards the white dwarf is maybe it got engulfed by the star, but it didn't quite get engulfed badly enough to completely be destroyed. And this is a scenario called common envelope evolution. So what I'm showing here is a simulation, and I'm going to click go in a second, and I'm going to show you what happens. Here's the star. You can see that the core is this green thing here, and all of this stuff out here is its envelope, the gaseous outer layers of the star. And it's puffed up really, really big at this point. So we're talking about the very largest extent of this star when it was about the same size as Earth's current orbit from the sun. And here's the planet. Here's WD 1856b. So when I click go, you'll see the planet start orbiting around, and it'll zoom into the gas of the star, and it'll kind of blast it all off, and it'll continue surviving. So this is the idea behind common envelope evolution, is that if you start to get engulfed, but you have enough heft, if you have enough mass, you can almost make it in and survive without getting completely ablated or torn apart by being inside of a star. This is kind of a tricky thing to imagine, and it's not an easy way for a planet to survive, but this is at least one possibility. So the other possibility that we like to think about is called high-eccentricity migration or tidal migration. So the idea here is that somehow, and I'll get into the somehow in just a second, your planet starts off on an orbit that is far away from the star, but then eventually changes its orbit so that it comes very, very close in a part of its orbit. So it zooms down here on a very elongated orbit. Let me zoom in real quick. And goes right around and whips around the white dwarf here. And when it whips around, it gets so close to the white dwarf that it gets stretched out just a little bit. And this is something that we see happening in lots of situations around main sequence stars, and it's similar to physics that we see here on Earth. So let me show you this video of a tennis ball bouncing. When the tennis ball hits the ground, it deforms and it gets stretched out. And that deformation, that releases energy. So some of the energy that that tennis ball had that caused it to fall down has now been converted into heat and lost. And when this tennis ball bounces back up or to where we've tried to release it from, it's never going to reach the exact same height. It'll always bounce a slightly smaller distance each subsequent time it bounces. It loses energy. So the exact same thing is potentially happening to this planet around the white dwarf. Every time it comes in close to the white dwarf and gets stretched, it loses some energy, and it doesn't return to the same height, the same distance away from the white dwarf as it did the previous time. If you do that for literally billions of years, then perhaps you can take an orbit that started off far away and very gradually bring it close in to where we see it today. Now the question is, if we want this to happen, we need to somehow get the star on an elongated orbit to begin with. And there's a couple of options for how this might work. So option number one is perhaps there's other planets in the system that we don't know about yet that got a little bit too close to the other planet, WD-1856b, and the gravitational influence of them could send perhaps one of them shooting outwards and the other one shooting inwards, and we get WD-1856b happening the way we think it, the way we imagine that it might have formed in this way. The other option is there's actually two distant red dwarf stars orbiting the white dwarf at a distance of about 1,000 times the distance from Earth's to the sun. And that's these two stars right here. They're called G229-20AB. We know those stars exist, and there are ways for their gravity to elongate the orbit of a planet like WD-1856b if the original configuration is just right. So there's a couple of different options for how you might get something like this. One of the fun things about studying the system is we really don't have any clue as to how this happened yet. There have been numerous papers written about the system since our discovery originally. And so far, the score is tied. All three of these different mechanisms have the same number of people claiming that this is the one that's most likely. So we have to see how to figure out what actually happened and how this planet moved into where we found it originally, to where we found it right now. So we have a couple of ideas of our own to try to tell the difference, and those involve taking additional data. So one thing that we've done is we've taken observations with the James Webb Space Telescope. We've taken two observations, one in April and one in June, and we're analyzing the data right now. And what we can use this data to tell us is how massive the planet is. We think that if the planet is relatively massive, then that implies that the common envelope, the idea that it's spiraled inwards through the outer layers of the star, that actually could work, because if there's enough mass, if it has enough heft, then maybe it could survive being inside the star like that. If it's low mass, then maybe it would be much harder to do so. But actually, the JWST data are showing us that the mass is actually high. So it's maybe closer to 10 times the mass of Jupiter, which means that maybe this spiraling inwards scenario could work. The other thing we can do is look for other planets in the system. So this is something that one of my students, Sarah Kubiak, who is now a graduate student at Colorado State University, is working on. She was studying whether we could find or rule out additional planets in the system by their gravitational influence on the one planet that we know. And so far, she's been able to say there are no planets in orbits that are relatively close. There are no planets in those orbits, which means that there are no planets that potentially could have sent that other planet inwards, but there's still a lot of space we haven't been able to search yet. So over time, we'll take more data. We should be able to rule out or identify any other planets that could have sent WD-1856 to its current orbit today. All right. So I want to leave you with one final thought, which is to talk about the habitable zone of the system. The habitable zone is a location in every planetary system where we calculate that water should be able to exist on the surface of a planet. So, for example, Earth is in the habitable zone of our own system because we have liquid water here. But Mercury is not, because Mercury is too close to our sun and therefore too hot. And Jupiter is too cold, and therefore water would freeze out there if there was a solid surface. So this is an idea which lets us kind of pinpoint where in a system life might be most likely to arise, because we think that the key to having life outside the solar system is to have abundant water like there is here on Earth. But interestingly, white dwarfs have habitable zones too. Even though the stars themselves are dead, they still could have enough heat left over from the fusion of the progenitor star, the kind of leftover heat that causes it to glow, to heat water on a planet very close in. And if you look at where the habitable zone is in the system, it's right around here. So it turns out the WD 1856b is actually very close to the habitable zone of this white dwarf system. And that's interesting because the habitable zone is in this location where we think it's really hard for planets to exist unless they come in later, like WD 1856b has. So if WD 1856b could survive the journey from far away to close in, maybe a smaller planet could as well, and maybe even a rocky planet where life could arise in the system, even after the star itself has died many billions of years ago. So with that, I'll put up my conclusions, which is that TESS is working great and we're making new discoveries every month. We found thousands of planet candidates. Hundreds of them have already been shown to be real, and we're working hard on confirming as many of the rest as we can. And the planets that we're finding with TESS have already taught us new and exciting things about the diversity of planets in our galaxy, and maybe have even given us a glimpse at the future of our own solar system. And with that, I'm happy to take questions. Thank you.
That was great. Thank you so much. So I think Q&A can be interactive. If you all want to unmute yourselves and ask your question yourself, or if you want to put it in chat, I'm happy to relay it. And I'm also, I forgot to mention in the beginning that we have been also streaming this talk live to YouTube. So I will take a look at the YouTube chat as well if any questions have popped up there. But meanwhile, if you all have any questions in this Zoom video call, like, go ahead.
Yeah, I have a question. This is a very nice talk and a fascinating area. I'm just wondering, since I've kind of followed this as an amateur astronomer, for a while, I'm just wondering, there's been a few articles out on the 10 most likely planets within 50 light years of the planet Earth to harbor life. And since this is your life, so to speak, doing this type of work, I'm just wondering on your batting order of stars and planetary systems that are pretty close to us, somewhere within some sort of reasonable radio communication distance and so on and so forth. I'm wondering, what would you say would be the top three systems that are the most interesting to you?
Yeah, for me, the two that are most interesting are Proxima Centauri, just because of the proximity, and TRAPPIST-1. And the reason why TRAPPIST-1 is kind of overall just so enticing to us is because not only is it got multiple planets in the habitable zone, but they're the ones that we might actually be able to search for biosignatures. So you alluded to one way to search for life, which is looking for technology, right? Communications, radio waves from potentially, technological civilizations like ourselves. But what I'm, and I'm very happy to look for technosignatures. But what I'm always nervous about is how unlikely it is to find technosignatures at any given time in the history of a planet. So if you look at our own planet, we've only been putting out radio signals for the last 100 years or so, and our planet's been around for 4 billion years. So that means that if you were to randomly select a time in our planet's history, only 1 in 10 million chance that you would find technosignatures if you looked at Earth. But if you want to look for biosignatures, like any signs of life over the entire biosphere, then that chance is more like 1/2. So what I'm really excited about is looking for the biosphere, looking for evidence of like ozone and oxygen and methane, all in proportions in the atmosphere that we wouldn't expect otherwise. And that's why those two stick out to me. TRAPPIST-1 because it transits, so it has that favorable geometry, so we can search for evidence of its atmosphere by seeing like how much light grazes through the planet's atmosphere when it goes in front of the star. And Proxima because it's so close by that we could potentially either take images of it or even send spacecraft to it and look for, life the old-fashioned way, even if it's not going to talk to us with a radio telescope or with a radio transmitter.
That's great. You're completely concordant with Astronomy Magazine on those two.
Yeah.
So I guess must be common knowledge. And so it would be spectrographic profiles of the stars that would pick up so is ozone the #1 candidate for a signature?
That's a great question. So this is something that kind of changes a lot, and I'm not sure what the most attractive bias marker is today, but usually it's not just one molecule, it's a combination. So the idea is like maybe there's one way to produce like a lot of ozone, but it's hard to have a lot of ozone and there's a lot of methane and there's a lot of O2. So the combination that gets the most play is O2 and methane, because those two things should react violently and quickly if they are both present, unless they're being continuously produced. And then I think once you see those two, then you go look at ozone, because that one's a little bit harder to actually observe. I think that's kind of the current consensus, but that's also all very subject to change. Those are the three that really show up best in the spectrum, though, of Earth today. Earth was different many years ago, so that's another kind of dimension we're looking at. Is like, okay, well, what would Earth have looked like in the Archean era? Would there have been very different looking biosignatures, and would we want to have different strategies?
Well, thanks very much.
Sure thing.
Excuse me. Any other questions? Oh, I think I see a message in chat from Sachin. Excellent talk. Thank you. My microphone is not functional, hence typing the question. How do you start from the images by TESS to finding likely planets? Do you start by looking at flux over time for each of the dots you see in the image?
Yeah, exactly. So the first step is we take the images and we measure the flux from each star. And we do this for each set of images. So TESS takes images every couple minutes. And in each of those images, we measure how much light is coming from them. Then we compile them all into those time series. And then we do automated time series analysis called Boxley square search. It's essentially, it's like a Fourier analysis where you try to take a light curve and look for periodicities. And if you see something that looks like a dip that happens over and over again, then it produces a strong detection in this Boxley squares search. And we essentially just do that millions of times each month. Originally, we started off using CPUs to do all of this, and very quickly we ran out of CPU power. So now we've moved over to GPUs, and that's really helped speed it up quite a bit. And hopefully that will increase our sensitivity as well, because we'll be able to be more thorough in the search.
That's cool. Is this something that can be done by citizen scientists?
Yeah, so there's a long history of citizen scientists looking for these types of signals. So what I mentioned, this Boxley squares, that's looking for periodic signals, which means you need to have the signal repeating. You have to see the transit happening over and over and over again. But humans are actually very good at seeing them even just once. So that's where the citizen scientists have really been contributing a lot and thriving in the ecosystem, is looking for the planets that we're not able to get as easily with the computer algorithms. We are talking about millions of light curves, so it takes a long time to go through them. But there's some and very impressive citizen scientists who've literally gone through tens of millions of light curves by eye and found tons and tons of really cool stuff. So it's really an awesome way to contribute.
If I could just say one thing on that, I have a reasonably good observatory, and I've tried to do that, and there's software that's available which automates most of the process. But the problem I had with these periodicity is simply the scintillations of our stars in the Bay Area here. I mean, I looked at those images you had there, and I said, geez Louise, I don't see anything like that. It's just, the noise is so bad with the atmospherics that you have here. It's obvious why this is being done in space. Although people can do it and do it, from dark sites. But like for those of you who are astrophotographers, if you go out on AstroBin, you'll find people who do this almost for a living, so to speak. And they're very helpful, but they can't change my atmospherics. So I gave up on doing it. So unless you can shoot my telescope into space, I think I'm sunk.
Yeah, you can't beat going to space. It's just a cheat code. But it is really impressive how much you're able to do from the ground, as you mentioned, at those dark sites. For decades before Kepler, people were finding planets using camera lenses like in Arizona. And they weren't finding anything near as sensitively as TESS and Kepler, but they were able to find planets, which is kind of amazing when you think about, how much the atmosphere really messes you up and how, tiny those lenses are.
One thing it's interested me has been the use of AI in amateur astronomy. I'm sure you use it, and just in the last year or two, it's really taken off with noise reduction and a lot of techniques. But I need to go back and take a look and see whether someone has applied AI to those curves, those transit curves, because it would seem to me that would be ideal to train on and to optimize the type of software that's used to detect those signals. Anyway.
Yeah, in fact, we actually use AI in the downstream part of our pipeline. So once we identify the dipping signals, we get lots and lots of non-planets and a very small number of planets. So our first step is to send it through an AI pipeline and triage it to get rid of, 90% of the worst signals and leave only the best ones that then humans can go look through.
Any other questions or comments? Okay, let me check the YouTube chat once to see if there are. Nope, no questions there. Well, I guess then we can wrap it up, and it's getting really late for Dr. Vanderburg, so we should respect that. Thank you so much for joining us all the way from Boston, and we really appreciate that. And thank you all for joining as well. Hope you like the talk. And if you have any questions that you think of later, you can always email me, and then I'm happy to pass them on. And with that, have a good weekend. Oh, I see one comment. Oh, great talk. Thanks again. And then I'm just gonna stop the streaming over in YouTube. And